I'm Alok. I work in the Red Hat storage business unit as a product manager. I look at the core Red Hat cluster storage requirements and downstream releases. And we'll talk about storage for containerized applications. What are containers? How they are different from virtual machines? Why we need persistent storage for containers? And what we are doing at Red Hat to enable containerization. So DevOps, this is probably a term which many of you may be already familiar with. It's not an English word, it's amalgamation of two words, developer/development and operations. And traditionally, if you see, most of the DevOps folks are have been separated by organizational and process boundaries. And they aim to do better, they intend to do better with better collaboration, communication, integration, and obviously automation. So how does container help DevOps to overcome the challenges, right? Containers, as it has been previously explained by some of my other colleagues, right? So container is nothing but a software packaging concept where you include the application and all the runtime dependencies, libraries, binaries, etc. As you can see in this block diagram, you can have a server, host operating system, which can be a Linux operating system. On that, you can spin up multiple containers, right? The benefits, what it provides to a DevOps environment is, let's think of a scenario when an application gets developed, right? So when the application gets developed, it is developed in a developer's sandbox environment, right? So it is developed and designed to work in a specific environment. When it moves to test environment or when it moves to operations, at times it doesn't work as desired. It doesn't work as expected, right? And then the developer comes back with the standard reply that, oh, it worked fine in my setup, right? So containers intend to resolve this age-long problem of, oh, it worked fine in my environment, in my sandbox setup, because a containerized application is intended to work, is designed to work in multitude of platforms. So it results in higher quality software releases and obviously shorter test cycles because there is lesser back and forth communication between dev and test. And for the operations guy, it results in the easier management of application because the containerized application gets deployed and works nearly flawlessly in operations. Yep, sure. This one? Yep. Mm-hmm. Yes, the shared one. Right. Okay, so let's say you have a RabbitMQ messaging application, right? So only the libraries which are required to get that RabbitMQ application up and running will be needed, right? And on container 2, which it can have a MongoDB database, right? And only the libraries and binaries required for that application will be needed, and underlying operating system will be shared. So if you look on this slide, it is more clear, right? Where we talk about host OS and shared services, right? So you don't need any kind of virtualization layer? No. So that I mean that was a very valid question, and we were progressing to this slide, right, where we talk about why we do not need a hypervisor layer here, right? So if you can see here on the left-hand side, I have the server, host operating system. On that, you have a hypervisor layer, which is nothing but a hardware emulator. So when you create multiple virtual machines, right, you create multiple virtual machines, you need to install dedicated operating system. It can be Windows or Linux or any other operating system supported by the hypervisor platform, right? And If you look on the right-hand side, when we talk about containers, so here is a server, host operating system with the shared services, and you can spin out n number of containers, but the major difference between virtualization and containers environment is that in containers, you do not require dedicated operating system per container, right? So that's kind of biggest difference. Yep, please go.
Continuing with this question, so you said that it doesn't require a specific OS, right?
Right.
So, but suppose if I have application which is developed for Windows, can it will be reside simultaneously with Linux application?
No, so containers that we are talking about here are LXCs or Linux containers.
Only Linux containers.
Right.
The libraries will be for Linux. Basically.
Right, that's correct.
No Windows application will be going to in that container.
No, any application which can work on multiple platforms,
Okay.
if it can work on Linux platform as well, then you can containerize it, right? Yep.
Thank you.
You mean
Even SAP kind of application I can run like this by
Uh,
making container SAP,
SAP?
SAP, you know, my
Right.
SAP application
So-
I can run like this.
Yeah, so we are still very early in this game, right? So I will also talk about stateless and stateful applications.
This is not released for commercial use as of now. This container.
So containers have been democratized and standardized by open source project called Docker. What we are doing at Red Hat is enabling all the applications, stateless as well as stateful applications, to get containerized. And we are providing the backend storage for that. Yeah. So yes, SAP is a stateful application, right? So when you talk about SAP or similar applications, you need to remember the previous transactions, right? So the current transactions are dependent on previous transactions, which requires persistent storage, and we'll talk about it, right? So containers are pretty much there, right? But enabling containers with persistent storage or the stateful applications which require persistent storage, that's a work in progress, right? And we'll talk about all of it. Yeah, so containers results in faster instantiation. Yeah, please go ahead.
So from the OS, how it does I/O network and process management from
That's a very
perspective?
good question. And so if you look at the host OS and shared services, right? So for Linux containers, LXCs, there is a concept called as C groups or control groups. So control group, what it does is that it does kind of quality of service for every container, so you can assign dedicated resources for every application depending on what all resources are required by any application, which has to be containerized. So C groups take care of the resource consumption part.
Okay, if there is any vulnerability in the guest OS, then it will affect the containers also. Because
I'm sorry, I didn't get it.
like if there is any library problems in the guest OS, like Red Hat Linux, then they will affect the containers hosted on it.
So there is no guest OS here. So guest operating system is on the virtualization side, right? When you create a this is the major difference between virtual machines and containers. So when you create a virtual machine, you install guest operating system on it. When you create containers, there is no dedicated guest operating system.
But there will be a operating system.
Yes, so this is the second layer, the host operating system, shared services.
Yeah, that will be in case there will be any vulnerability on that host OS.
Yes, so if there is a dependency, right? So let's say you want to make some changes in the application, and then you get into a case where you are getting some dependency failures, right? So then you need to resolve those dependencies by adding them on the second layer, on the operating system layer.
Okay, then the downtime will be required for all the containers too.
No, because, okay, it's as simple as when you, what happens when you update RPMs, right?
There is a security patch apply or reboot the patching of that OS.
So any okay, so any patch update which requires reboot of the server right, will be there. But if you have a persistent storage, right, let's say you have, so we'll come to that part, right, but just to give you a background. So in this case, where you have your server, right, below that there will be a storage layer, and which will span across multiple nodes. Let's say you have to bring this node down, right? So the storage will have volumes carved out of it, which will span across multiple layers, which will span across multiple servers, right? So this one goes down, high availability will be provided by persistent storage.
Okay, that will be hosted on another node.
No, it can be hosted on another node, it can be hosted on the same node as well. We have two deployment topologies that will come in the later part of this presentation.
Okay, thank you.
Yeah, thank you. So, better isolation, as the gentleman there asked the question. So, it gets provided by something called as C groups or control groups. And then easier scalability is, again, you can spin out n number of containers, right, on a single server. And you can also scale when you have persistent storage. So, what do we see here, right? A gigantic truck. So when you think of a bare metal physical server, it's pretty much like a gigantic truck. It requires a specialist driver to operate this truck. This has a huge footprint, right? So this is very similar to a bare metal server. When you think of virtualization, you have these large number of cars. Every car has a dedicated engine, right, which is very similar to a dedicated guest operating system per VM. The overall footprint of all these VMs together can be similar or even greater than the overall footprint of a bare metal server, which is represented in the form of a truck over here, right? So, and each of these cars will need specialist drivers to operate, right? So we see trucks with large footprint, and we see the cars with something similar, where the footprint is very similar. And then we have containers, right? Just hop on and scoot. So the advantages you get over here is that it's lightweight, right? Containers are lightweight, and they are easily deployable. You don't need people with specialized skill sets to operate the containerized images, right? To operate the Docker containerized images supported by Red Hat. So what are the market dynamics, and why has containers got everyone thinking, right? Not just within Red Hat, but outside Red Hat as well. Within the industry, there is a lot of buzz around containers. So it has always existed. Containers have been there for more than 10 years now, right? So it has been there in the open source community in the form of LXCs for Linux container. Those of you who are familiar with FreeBSD may know that there is a concept of jails or JLS for FreeBSD, right? Which does storage containerization for multi-tenant environment. And then Solaris always had zones, which is another form of containerization, right? So Docker, as I mentioned earlier, is an open source project which standardized and democratized container technology. So if you look on the graph for Linux containers, right, it has been there. Linux containers have been there for more than 10 years, and it followed a haphazard pattern. There was a growth, it followed a haphazard pattern, and you needed people with very specialized skills to operate those containers. Now, if you look at Docker, it has grown tremendously over the last 2 years, last couple of years, right? And the growth is linear, but it's not haphazard. And for obvious reasons, it allows for more collaboration and automation between dev and ops, right? So a developer writes applications, it works in multitude of environment. It is supposed to work seamlessly and flawlessly in the operations environment, even if it is a different environment than developers' sandbox environment. So when we talk about containers, another keyword or buzzword which we hear very often is microservices. So let's look at some visuals to understand the microservice. I can define microservices in this forum, but that will be way too geeky and technical, right? So what do we see here? And by the way, this is not a food show. I haven't switched my topic, so still pretty much on containers. This is noodles or spaghetti, as we call it. So here everything is intermingled, right? So this is early 90s style of coding, where we used to use a lot of go-to statements, and it was nearly impossible to maintain this code because of this intermingledness, right? So then we move to the monolithic architecture, Lasana, right? It's a snack where you have multiple layers, right? And if you make change to any layer, then any other layer is also likely to get impacted, right? So this was the Lasana-oriented architecture with which we continued till late 2000, right? And then over the last few years, some of the large internet companies, they have moved to a ravioli-oriented architecture, or what we call as microservices architecture. So here you see there are multiple components, right? But if you remove any one component, it will have least or almost no impact on any other component, right? So this is the microservices architecture, and a question to ask is, did containers become prominent because of microservices architecture? The answer is yes, to an extent. Another interesting theory we have is pets versus cattle. So what happens when your pet falls sick? You take the pet to the specialist vet surgeon, right? Your pet needs all kind of love, warmth, and affection, and they always come in limited numbers, right? But when you think about cattle, so they come in herds, right? So they are self-sufficient most of the time. You don't need specialists to look after them. They are pretty much on their own. They are easily replaceable, and they serve a single kind of function, right? So when you think about virtual machines or physical servers where you host your applications, they are similar to pets. When you think about containers, they are pretty much on their own, and they are similar to cattle. So we discussed during the question about container failure, right? What happens when you update the packages and you have to bring down a host, right? Then all the containers will go down. Now, to solve that problem, we have persistent storage. So you have a persistent storage. It can be a Red Hat cluster storage, and you create a volume which spans across multiple nodes, right? So you have your node, which a cluster storage node, which co-resides with the application container. It can go down, but still the clients will continue to get served with other nodes, right? Which is always there because of the high availability and distributed nature of storage, right? Persistent nature of storage. Scale and high availability. So those of you who are familiar with distributed storage may know that so you can have n number of nodes, right? And it provides n-way availability. So you can have two-way replica, three-way replica, etc., and you can get the availability on that scale. So what are we doing at Red Hat to simplify container adoption, right? So what you see here on the screen is something which we call container zone within Red Hat. So this is Red Hat container zone. This has 4 pillars with which you can learn, build, certify, and distribute your containerized applications, right? So you have Red Hat Connect program for technology partners or independent software vendors, ISVs, and with that you get access to the tools to learn about containers, and you get the pre-release bits of the Red Hat software, right, before it before it becomes generally available, and then to enable the developers to write containerized applications, we have container development kit. Once the containerized image is ready, right, before it can be pushed to production, before it can be given to the customers, you need to test and certify it. For that, we have the container certification program, and all or any container image which gets certified can participate in the Red Hat registry. So once application container image is in Red Hat registry, you can use a set of commands from, or mostly a single command from Docker to get it up and running. Are we good till here? Yep. Okay. So, software-defined storage. So how many of you in this room are aware of storage, the traditional storage? It's pretty good. And how many of you are aware of software-defined storage? Right. So when we think about proprietary storage, right? So legacy hardware vendors, right? When they ship storage, they ship hardware along with the software. So you get a couple of storage processors or storage servers or storage node or service processors which comes built in with storage operating system. Now the set of controllers, I'm using the word set to indicate that even they provide high availability, right? One node goes down, another can come up. And those controllers are connected to large number of disks, right? Connected to large number of disk shelves, which contains disk. It can be FC SAS, NL SAS, SATA, ATA, or even SSDs, right? But when you think about software-defined storage, so you get an operating system, a storage operating system with a file system. You can install that storage operating system on any standard supported x86 server, and that converts the standard server to a storage controller. Then you can make use of the internal disk, right? And then you can add n number of such nodes. You can add n number of servers on which you can install the storage operating system, right? And the software-defined storage will aggregate the performance and capacity, which is not the case with the traditional scale-up architecture of proprietary hardware. Let's say you have a proprietary legacy storage hardware, right, which comes built in with software. Let's say you have a application which is performance sensitive, and the storage controller has cores, has CPU cores and memories just like any other server, and because of the performance sensitive nature of the application, your cores get maxed out, or your memory, your RAM of the storage gets maxed out, or the capacity gets maxed out. In that case, you cannot just scale it out, right? You cannot just add another set of nodes. Once it reaches the threshold of capacity, once it reaches the threshold of performance, you need to invest in another set of controllers. And there are ways to manage them together, but there is no way with which you can aggregate the performance and capacity of all the traditional hardware storage boxes which you have procured, which is very different from the scale-out architecture of software-defined storage. And for the obvious reasons that the traditional vendors ship hardware along with software, so the features and functionalities of the traditional storage vendors are tightly coupled with hardware, which is not the case with software-based storage, right? The features and functionalities are independent of the hardware in most of the cases. And they follow a closed development process, so you cannot just go to a download link and start downloading or get the upstream bits of traditional hardware storage providers' software, right? Whereas in Red Hat, we follow an upstream first philosophy. By upstream first, I mean that there is an open development process because of which every single bug which gets fixed gets there upstream. Every feature, every functionality is there upstream. You can download the upstream bits and test it. You can add to the code. You can add to the documentation as a community user without paying for anything. And you can get into healthy debates or the mailing communities on the pros and cons of any feature, right, which gets productized as and when we make the product generally available as a downstream product. So, yeah, this will answer most of or at least some of the questions which some of you guys had earlier on what happens when a node goes down, why we do not have a dedicated guest operating system, etc., etc. So at Red Hat, to provide persistent storage for containers, we have two deployment topologies. So this is the first deployment topology, and the storage layer or the storage cluster sits adjacent or is independent of the atomic host cluster. By the way, some of you may not be familiar with atomic host. So RHEL atomic host is nothing but a customized version of Red Hat Enterprise Linux 7, which gets shipped with Kubernetes and Docker. So Kubernetes takes care of the orchestration, and Docker packages are used to get the containers up and running, along with serving out storage, right? So in this model, you have storage which is independent of the host cluster, and you have the RHEL atomic host in each of the hosts, right? You can have n number of application containers, and the storage can be served out from the independent storage, right? So if, let's say, your application requires block storage, your application has been architected in a way that it needs data isolation. So for providing block storage, we have Red Hat Ceph storage, right, which also has a S3 interface, right? And if your application has been architected in a way that it doesn't need data isolation, right, it wants the file share to be visible across n number of application containers, then Red Hat cluster storage is the right solution. So coming to the second model, this is the hyper-converged model. The reason why I'm calling it hyper-converged is if you look at this model, storage is outside of the host cluster, right? In this model, storage is sitting within along with the application containers. Storage is co-resident with application containers, and storage here is nothing but just another container. So you can bring up a container in which you would have installed Red Hat cluster storage, right, along with Kubernetes, and Red Hat cluster storage makes use of the local storage, and it can co-reside on the same node on which you have your application containers, or the application container can reside in a different host, and then you can either do an NFS share, or you can provide a fuse mounted storage to the application containers. How it all works, just to get into the nitty-gritties, so you can make use of a single line Docker command called docker pull to pull up the containerized image from the registry, containerized Red Hat cluster storage image from the registry, and then you can make use of another single line Docker command called docker run, which will get the container up and running. And what it also does is it serves the storage from the local server to the Red Hat cluster storage containers, right? So that's pretty much it from me. And if you have further questions, you can ask now, or I'll be around in the same area. We can meet and talk about what we can do to resolve the challenges you have with containers. Thank you.